Okay, welcome back everyone. So today I'm going to be doing a video on some number theory, and specifically it's going to be regarding the properties of order mod some integer n. So today we're going to show the following property, and that's the fact that the order of an element A is a divisor of phi of n, mod n, where the GCD of A and n is equal to 1. Now, I just want you to quickly recall that phi of n is essentially just the number of numbers coprime to n that are less than n, right? So, and also recall that order is the smallest integer. Let's say it's the smallest integer d, such that so the order of a is the smallest integer g, such that a to the d is congruent to 1 mod n. So the order, this is said to be the order of a mod n. Okay, and because we'll actually be using this in our proof, I would like to briefly prove Eulers Theorem. Actually, first I'll give the motivation for this GCD equals 1 here. Because suppose that the GCD of n, a and n is not 1. Then we have that if d is the order, or essentially any value such that so we're assuming that the GCD, by way of contradiction, the GCD of a and n is not 1. So a to the d is congruent to 1 mod n, right? So then that implies that a to the d, and actually we'll write a as essentially being, well, some constant times, let's say, q1, right? So, and also we'll have n equals some constant k times q2, where k is some value that is not equal to, that is greater than 1, and that's going to be the GCD of a and n, right? So this directly follows from this. Okay, so now we'll write this as an equation. So we have that k to the d, q sub 1 to the d is equal to k to the d, or sorry, k times q2 plus 1. And that implies that 1 is equal to k times some other stuff. But the key thing here is that 1 is a multiple of k according to this equation, which is not true because, well, we're dealing with integers, right? So the only possibility for k really would be 1, but we assume that k is greater than 1, so we reached our desired contradiction. Thus, the GCD of a and n is exactly 1. Okay, so now let's get to the Eulers Theorem, and Eulers Theorem states that with this condition, a to the phi of n is congruent to 1 mod n. So I'll prove this real quick. So we note that, again, phi of n is the number, although I won't write it out, it's the number of integers greater than 0 and less than n that are coprime to n. So let's say that set of integers is going to be r1, r2, all the way to r sub phi of n, since there are phi of n such values. And I want you to consider, so let's say this is the set S. I want you to consider the set A times S, which is equal to A r sub 1 all the way to A r, and I should say that, actually, to avoid confusion, I shouldn't use A, since we're already using A. I'll say B. B, actually, yeah, we are using A, since, yeah, so I should bring that back. So AS is the set A r sub 1 all the way to A r sub phi of n. Okay. So now I want to let you notice that, well, these account for all of the, so if we reduce this mod n, right, this will account for all possible values, all possible residues mod n of values that are coprime to n. And since the GCD of a and n is 1, these values are all also co-prime to n. So as a result, this set must lie inside of this set here. Now, the last thing to show is that that we wish to show is that, well, this set is a permutation of this set. So in order to show that, we want to show that all of these are distinct, like these are. And if we assume that they're not distinct, or, well, if they're not distinct, then a sub r sub 1 is congruent to, or in general, a sub r sub I is congruent to a sub r sub a times r sub j mod n. But since the GCD of a and n is 1, then it has an inverse, so we can take away these. And that implies that we have injective map here, which is good. So that tells us that this is a permutation of the set. In other words, these sets are equal mod n. And what that tells us is that, well, if we multiply all of these values mod n and set them equal to each other, well, they're going to be congruent to each other mod n, since the sets are equal. So what I'm trying to say is that let's let the product of all of these terms be equal to capital R. So we have R is congruent to, and then how many a's do we have? Well, we have a to the phi of n a's times R mod n. And since all of these elements are coprime to n, R is also coprime to n. So R has an inverse, and we can kind of cancel these out. And that finishes the proof, because we have a to the phi of n is congruent to 1 mod n. Okay, so that is what we wanted to show. So now let's get to the finale of this proof. So, show that the order of an element A is a divisor of phi of n mod n, where the GCD of a and n is 1. So suppose the order of a suppose order of a is d, right? So that tells us that a to the d is the smallest value, such that a to the d is congruent to 1. And I will note that d is not 0. That's not allowed. Mod n, right? And by Eulers' theorem, we also found out that a to the phi of n is congruent to 1 mod n. Now, if we set these two congruences equal to each other, and since, well, phi of n is strictly greater than or is greater than or equal to d, since d is the order of a mod n, then, and since also a to the d must have an inverse, since a to the d is also going to be it's also going to be coprime with n, then we can essentially just take an inverse of a to the d on both sides, and we'll arrive at the fact that a to the phi of n minus d is congruent to 1 mod n. Okay, but notice that we can keep setting this equal to this, and until we get something that is less than d. And notice that that is just the definition of dividing things together. So why don't we use the division algorithm and write phi of n as some multiple of d plus a remainder. So we have phi of n is equal to d times some q plus some remainder, where the remainder is a member of the following set: 0, 1, all the way to d minus 1. Right? Okay, well, let's plug this back into our Eulers theorem. And what that gives us is a to the d q times a to the r, which is congruent to, well, notice that this is a to the, this is the beautiful part, a to the I should say a to the q to the d, but by definition, by definition, this value is actually going to go to 1, right? So this value is going to go to 1. Okay? And furthermore, and notice that we're going to have notice that we're going to have a to the r here, which is congruent to 1 mod n. Okay? But since this is a to the r is congruent to 1 mod n, the problem arises that r is actually less than our d here, but it can be equal to 0. But if suppose it's not equal to 0, then it's going to be the new order, but it's going to be the order, but we already set the order to be d. So in other words, it must be 0. And it directly follows that if we plug r equals 0 into here, we get that phi of n is some multiple of d, and it directly follows that d divides phi of n, which is exactly what we wanted to prove up here. So I will smack that QED sign up there, and I hope you enjoyed the video, and have a nice day. Goodbye.